I'm back. All right, we're working on TIG and we're looking at the parts of the torch. I know it seems kind of confusing, but hang on, okay? So we're going to start with the back end of the torch. The first thing we're going to look at is the hoses, or what comes in and out of our torch. This is going to tell us a lot about the torch, okay? So if we look here and we have two lines, this is our power and our gas. Or we can have a power and gas line together. Newer torches are just having a single one. This is an air-cooled torch or a gas-cooled torch. Now, if I see that there's three lines, a gas, this is going to be power and water return, and another one strictly for water. And some of them now are actually being combined, with power and gas, and then a water up and down. Okay, if we see three lines, we know this is going to be water cooled. Okay, and I'm gonna put up a little note for our welding tips and tricks for the video on different types of torches, how they rate them, like for the numbers and how to choose one and things like that. Jody has a lot of really cool stuff on that, so I'm going to put that up for you guys. Okay, so if you're using a water-cooled torch, you want to make sure that your intercooler or your radiator is on prior to welding, okay? We don't want to burn up the torch. You want to also make sure that every time you weld, you check and see if there's water in there. You also want to check and make sure there's no leaks or burns in your hoses, because if it leaks all out, you can burn up the pump too, okay? So, how do I know that somebody's going to use an air-cooled torch over a water-cooled torch? Well, most guys are going to use an air-cooled torch for anything under 200 amps. Okay? If you're using a lot of, like maybe we're doing production work and we're making a lot of little welds, even though it's not really, really hot, it's going to start to put a toll on your torch. So you might want to get a water-cooled torch for things like that. Now, if you're going to be running above 200 amps in the majority of what you're running, you're going to want to have a water-cooled torch. I prefer water-cooled torches even if I'm not running high amperages, because I know it's cooler and I prefer it, okay? All right, so in order to set up the torch, we need to know what's the top and the front and the bottom and the back, okay? So if you notice, there's a bottom and a top. And when you look at a torch, there will actually be numbers right here, okay? We want the numbers so that you can read them, okay? That tells us what's the top and the bottom, okay? So it won't, sometimes some of them, they kind of look the same, so we want to make sure that we can read the numbers, okay? So first part we want to look at is the gas nozzle. This is also called the cup, okay? This is a pink ceramic cup. And we want to make sure that we look at it, check it out before we put it on. We want to make sure there's no cracks or chips or anything in the cup. If this is where the gas is going to come out, it'll get hot from welding. So if it's damaged, it can fly apart. But if it has a crack in it or a little chip and it hasn't broken apart yet, we can also create turbulence in our gas. Okay, so we don't want to drop it. We don't want to throw it across the room because it will break. All right, you can also use a small, they have white ceramic, and they also have Pyrex that you can see through it. But let me tell you, those Pyrex cups are super expensive. I think one guy paid $60 for a Pyrex cup, and something happened. It rolled off his table and it broke it, and he only used it once. Okay. So gas nozzles are cups. They come in a lot of different sizes. And let me see here if I have a picture. So here are the nozzle sizes here. They come in 1/16 of an inch, so a number 6 cup is a 6/16 of an inch. Okay. All right. So the collet body, right here. Okay. This is the collet body. This is made of brass. Okay. This will screw on to the bottom part of the torch right here. This will screw on first. Okay. You only need to make this hand tight, just snug it. Any tighter than that, you risk not being able to take it off, or having to take it off with pliers and damaging the collet body, because this is pretty much a bunch of threads. Okay, and remember, it's brass. It's going to get hot, and when it gets hot, it's going to expand. Okay, and it will get tighter. All right, so we're going to put the collet body on, and once we put the collet body on, we're going to attach it here. Then we're going to screw on the gas nozzle. Okay, now after that, we're going to put on a gasket. It makes it easier if we put the gasket on first. Some torches, they have a built-in gasket already. Some of the older torches require one. So we have a couple of different ones in the shop. Some require it, some don't. But you're going to pop it on over here, and there's kind of like a little indentation that you push it into. Okay. Then the next part is the collet. Okay. I'm going to try to describe this as best I can to you. But pretty much what this is a cylindrical piece of brass. Okay, and it has little slits on it, and it has a little collar on the top. So when we put our tungsten in it and we crank down the back cap, those little slits close and it holds the tungsten. So what'll happen is this collet will be put in from the back here, and it will go into the collet body. Then you're going to put in your tungsten, and you're going to make it stick out as far as it needs to stick out. And then you're going to put the end cap on, or the back cap, so it secures everything in, and that's all you got to do. Okay, we'll go over this a couple times in the shop, and you guys will be just ready to rock and roll. Okay, so now rule number 3 states that what? 90% of what we do, thickness of material dictates amperage, filler metal, and even in this case, diameter of tungsten. So we want to pay attention to this. We want to make sure that we have an adequate size tungsten, if it's not too big or too small, and it'll also help tell us if we have a big enough orifice. All right, so, come up here. We're running at 0.126. It's almost a little bit bigger than 1/8 of an inch, so a 3/32 tungsten we want to use, and that's what we're using. And then we have a number 6, so it's a 6/16, so we're within range for that. Okay. All right, so a gas lens. Okay, there's a lot of big debate about it, and this was a really big rage. They had started coming out a little bit more when I was in school for welding. Gas lens help direct the gas. It gives it less turbulence to the string. Doesn't mean you can't use it. It's just one of those things that's really helpful. Okay, so I couldn't afford a gas lens. So my mentor, he taught me how I can make one. So what we did is we actually put a piece of steel wool inside my cup, and it helped direct the gas. Pretty cool, right? Poor man's gas lens. So it just helps with the turbulence of the stream. Doesn't make it any better. If you're an okay welder, you'll be an okay welder. If you're a terrific welder, you'll still be a terrific welder. It doesn't change much, okay? All right, now we're going to come down to electrodes. Now, when we're talking about electrodes, we're talking about tungsten, okay? So, electrode. Electrode is something that carries electricity. In the case of tungsten, it carries the electricity without being a filler metal. Of course, if you use a tungsten that's too small for the job, the tungsten will deteriorate prematurely. And if you touch your tungsten to the work, it'll also shorten its life, and you have to replace it a lot sooner. So, let me show you something. Come on now. Oh, wow, that's really big. Come back, Jack. All right. I don't know if you guys can see that. Boy, this is just not happening today. Let's try this again. Okay, so here it is. Here's some electrodes that we have. So E is for, of course, you guessed it, electrode. W. W, W, W. W is the chemical symbol for tungsten. It's like wearing stromium, and that was the guy, the German guy who actually founded it. All right, so there's a lot of different tungsten here. And, well, these elements are alloying elements that give it ability to have higher temperature ratings or other characteristics to really help the welder. Okay? So we're going to use the letters, the chemical letters, T, H, L, A, C, E, Z, R, P, G. Any of those show us the chemical alloying elements, or the chemical symbol for these alloying elements. So EWTH is fluoridated. And the number after it, it tells us the percentage of how much of this alloying material is in there. So many different tungsten can be ran in many different currents. Usually they're going to say these run in a particular current, and it shows us which ones perform there. Okay. So personally, I use only two tungstens. EWTH2, which is the red band, that is thoriated. And let me tell you about that. Thoria, they say, is mildly radioactive. So for a long time, they were saying that you were going to get radiation poisoning and all sorts of stuff. The biggest thing is, as long as you don't sniff it while grinding and, doing lines of the grinding dust, you're fine. Okay? You can touch it. I've actually licked them before. Nothing happens. You're perfectly safe. Some people believe that they were really going to get radiation poisoning or something like that. So they came out with different types of tungsten. The other one that I use is EWP, or the green band, and that's pure. All right, you have a bunch of different ones. They got orange, they got gray. When we see a gray one or a purple, those ones are usually dealer choice, which means that the person or the company that makes these tungsten, they can be whatever they want, and it can come out kind of bad. I also have another welding tips and tricks on the tungsten. This one's super duper. He actually tests out different types of tungstens and really gives you a good idea. Okay, so tungstens, they come in different lengths and different diameters. Okay, it also tells us the current ranges. When we talk about this, if you use a tungsten that's too small for the job, it's going to deteriorate. It might melt down. It might not have enough amperage, or might be able not to carry enough amperage to what you're doing. So this helps us kind of give us the right idea for what we're trying to use in terms of diameter of rod, or I should say diameter of electrode. So we're talking about a 3/32 electrode. That's usually what, is industry standard. And it says if we're going to run it in DCEN, I can run it between 150 and 250 amps, okay? And I'm going to look, and it's telling us about different tungstens, which one I want to run. Now, if it says X, that's a placeholder for the percentage. It's saying whether we use EWTH2 or 1 or 1.5, it's still fine, okay? So if I'm using a thin piece of material, I don't want to use a very thick tungsten. We have to think, how many amps is it going to start the arc? And if we use a thicker diameter tungsten versus a smaller one, if it's too big and it needs a lot of amps to start it, then you might blow through your thin material. Okay. All right. We also have to talk about grinding our tungsten. Oh wait, boy, oh boy, this thing is just acting up today. All right, so we need to talk about grinding our tungsten, okay? We want to make sure that the grinder that you use is only used for tungsten. If something else is been ground on it, tungsten has pores. So if you grind it on something that's been used for something else, you can actually contaminate your tungsten because it'll suck up into it, okay? So when we grind our tungsten, we want to put the tungsten on our grinder, straight up and down, and roll it to sharpen it. We want to make a nice tip, but we don't need it pencil sharp, okay? We want to also avoid making the tungsten turn cherry red, okay? What can happen is it can melt the tungsten into like a little shell around the tip, and then when that tip and that shell get heated up when we're welding, a piece of the tungsten will actually fall into your weld and create tungsten inclusions, okay? So we know that the tapered tip is usually used for DC. Now, what about AC? Well, we want to use a rounded end, but as we start to get into the newer ages, we really don't need to. We can actually just have a tapered tip, and we can actually just knock off the top, okay? All right, so this is really important, guys, and I'm sorry this is taking so long, but electrodes stick out. Super important, okay? Stick out is from the end of the cup to my material. All right, I should say how far it sticks out my cup to the end of my tungsten, sorry. All right, so it's important. We need to make sure not only our weld and our filler metal is shielded by gas, but our tungsten too. If it's stuck out too far, it might not be shielded enough, okay? So the shielding also keeps your tungsten cool, and you can avoid other issues like oxidization and some fun stuff. Okay, so stick out is determined by the type of joint. For butt joints, listen carefully. We want stick out from 1/8 to 3/16 of an inch. And we tell you again, butt joint, 1/8 to 3/16 of an inch. Now, if we're going to use a fillet weld, like a T-joint, stick out should be 3/16 to 1/4 inch. Let me tell you again, T-joint or fillet weld, stick out should be 3/16 to 1/4 inch. So why do we need to change the stick out? Well, if you don't make it longer for your fillet welds or your T-joints, you might not be able to get into the root. You might not be able to focus the heat where it needs to go. And if you don't do that, you might get some bridging, okay? Meaning that it's going to connect. You're going to think it looks like it's all the way in there, but you have a pocket and it's a lack of penetration. All right, onwards, guys. I'm sorry this is so long. All right, let's go. Shielding gases. Okay, so the majority of welding is done with 100% argon. So we know there's always a time and a place. So we can also use 100% helium. Argon-helium mixtures are used, or argon-hydrogen mixtures are used, depend on what you're trying to accomplish. Okay, keep in mind though, if you use helium, it is lighter than air, so that means you have to turn up your gas to continue gas coverage. All right, what do we have here? We have backing bars. So what this is a backup bar, and what happens is we put our gas into here, and there's little holes cut into it so that we can make sure that the backside of our root weld, especially when we're doing open root with TIG, that we're protecting the backside of the weld. Well, what happens if we don't? Well, we're going to get what's called sugaring or black candy. It's ugly, it's nasty, it's gross, and it's contamination. Okay, so we use a back gas. Okay, and it protects things from atmospheric contamination. So we can also use a trailing shield to help get that gas behind it. And if we're doing something super mission critical, we have what's called the atmospheric chamber. I saw this when I was learning how to weld stainless steel. And this is the coolest mambo jambo thing I've ever seen. So what they do is they fill up this chamber with whatever gas that you're using, and it allows us to keep away the atmospheric contamination. It doesn't mean if you touch your tungsten to the material, it's not going to contaminate. It will, but it's super cool. Okay, awesome. Next. Okay, so we talked about regulators and flow meters. Okay. We use the flow meter because the machine doesn't regulate the flow of gas, okay, to the torch. So that means you have to use a flow meter, or how much is going to go into the gas. I should say the gas going into the machine. All right, so most power sources also have a remote control. You know, it's not like a little car, but it's a remote for the current. Allows you to change the current while you're welding. Most of them use a foot pedal, but nowadays they have a wireless foot pedal. Some of it's Bluetooth, pretty cool. They have a wired foot pedal. They have a finger controller, and they have all sorts of different types of remote current controls. But if the machine is a scratch start, it won't have any remote current control at all. So once the arc is started, the amperage stays the same through the weld. Okay. All right, almost there, guys. I'm working as fast as I can so you guys get this. Let's talk about classifications of filler metals. Well, does this look familiar? It should, because it's the same classification as MIG. Now, notice they say ER, electrode and rod. Well, the E is for electrode, right? But this is a filler metal. We're not using this as an electrode for MIG or for TIG, but we will be using it for MIG. Okay. R, rod. This means this can be a cut length or this can be a rolled length. Okay. Now, we know that the two numbers are for tensile strength in thousands of pounds per square inch. We have S as in Sam for solid. And the X here is our placeholder for composition. We can have a 2, 3, 4, 5, 6, or 7. And the most common is ER70S-2 for TIG. All right, remember, high frequency is used for starting with DC and maintaining the arc with AC. DCEN is used for most ferrous materials. DCEP is not used that often because it reduces shallow penetration and requires a really large diameter electrode. A water-cooled torch is recommended when we use currents over 200 amps. We also need to make sure that our water is flowing before we weld. If we use a gas nozzle or a cup that's too small for what we're trying to accomplish, it can overheat, crack, or deteriorate, aka make shrapnel. Alright, before we start to weld, we want to make sure the tungsten electrode has proper stick out at the end of the gas nozzle or our cup to make sure that we're going to get into the joint as necessary. The diameter of an electrode is determined by current, okay? We also know what? Thickness of material. And we also know that argon is most commonly used for shielding gases. Alright guys, take care. Bye!